In this video, we discuss some of the most essential lattices that we'll find in solids. Okay, so here's the idea. We're going to have a solid made out of atoms, and we're trying to figure out what way to pack those atoms into the solid lattice is going to lead to most efficient packing. Which one of the possible arrangements is going to reduce the voids in between atoms in that lattice? Well, there's many possible lattices, many different ways to pack atoms into a lattice, but the simplest one that you can think of would be something that we call a simple cubic packing. Okay, so suppose that you have here one atom, and then you can put 4 nearest neighbors, and then 4 next nearest neighbors. Okay, so this will be one layer of the solid, and what you have is that, again, notice that there's 4 nearest neighbors, and then there's going to be 4 next nearest neighbors that are a little bit further away. Right? So then you can put another layer on top of these, another layer, and that is what we call simple cubic packing. And I have a prop here to illustrate that. Okay, so that would be your unit cell for a simple cubic lattice. And this actually turns out to be not the most efficient way to pack spheres, because as you can clearly see, there's big holes, big voids in between those spheres. Something that is important moving forward is to recognize that in these models that we're going to be using to calculate packing efficiency, we are assuming that the atoms in that lattice are spheres that are rigid. Okay, and that is an approximation in our model. Right, so if this is not the most efficient way to pack spheres, which one is? Well, if you go to the grocery store, you can look at the oranges and the way that they arrange so that they minimize the voids in between them. And what you realize is that you have a packing in which there's a central orange, or a central sphere, and then there's going to be not 4, but 6 nearest neighbors around it. Okay, 2 and 6. Right, so notice that in this case you have 6 spheres surrounding the central one, and that packs much more efficiently than in this cubic arrangement that we have right there. Okay, so a way to illustrate that would be this. Okay, so this would be that type of arrangement. I have another one. It's a little bit more illustrative, right? So that would be this arrangement where you have, again, 6 nearest neighbors. In this case, you would only have 4. Okay, so that's actually the most efficient way to pack spheres in one layer. Now the question is, how do we actually then take this single layer and then go on to build a 3-dimensional solid? Right, so we're going to do this with models just to illustrate how that works. Right, so the second layer, which is what I have right here, is going to be right, those atoms are going to be right on top of the voids left by the first layer. Okay, so notice what we have right here. Those atoms are going to sit in those holes, and that will be the second layer. Okay. Now you're still minimizing the voids in between the layers. Okay. Now the question is, well, what happens when you put the third layer? Okay, and to put the third layer, there's going to be 2 different positions, 2 different locations, and that is going to give us 2 possible packings. Okay. Because this is the most efficient way to pack spheres. We call this closest packed lattices, and again there's going to be 2 of those. Let's take a look at the first one. In the first one, what we actually do is we take this first layer that we have right here and we put it on top of the second, such that the first layer and the third layer are right on top of each other. Okay, so if I now take this layer, which is exactly the same as the bottom one, right, those 2 are identical, and then I pack these ones such that the top one is right on top of the bottom one, right? This is what I called hexagonal closest packed lattice. Okay, and again, the distinguishing element is that you have groups of 3 layers, and the first one and the third one are identical, right? The atoms in the third layer are identical to the atoms in the first layer. You can rotate that around and see how that still is reproduced throughout. Okay, so that is one of the ways which we call hexagonal closest packed lattice, and usually is represented with the letters HCP. Right, and this is one of the 2 possible packings that leads to maximum efficiency. There's no way to pack spheres in a more efficient way than this. All right, but there's another one that is equally efficient, and that will be a cubic closest packed lattice. All right, so how would that work? Well, it turns out that on this layer there's actually two types of voids to put this third layer. Again, the hexagonal HCP lattice, we put the atoms so that they're on top of the first layer, but then there's actually a second type of cavities right here, in which now you cannot see it very well from the camera, but this atom in the third layer is actually not right on top of that one. They're a little bit offset. You can turn this around and you perhaps can see it a little better, how that atom is actually not right on top of this one. Okay? So now what will happen is that these are three different layers, okay, but the fourth one that you could put right here would be right on top of the first one. Okay, so this is what we called a cubic closest packed, and then that has the letter C, C, P. Then we can distinguish this because this corresponds to a packing A, B, A, B, A, B, but this will be A, B, C, A, B, C, and so forth. And again, in HCP, the first and third layers are exactly the same. In cubic closest packed, the first and fourth layers are identical. All right, so these two packings that are the two possible closest packings, and again, those are the ones that minimize empty voids. As a matter of fact, the amount of unoccupied volume in these lattices is 26%, right? So 74% is occupied by atoms, and that is, again, the most efficient packing that you can get. Now, that contrasts with cubic packing, which, as simple as it is and easy to understand, is actually not very efficient. All right, so in the next few videos, what we're going to do is we're going to be taking a look at not the lattices, right, so the three-dimensional solids, but instead we're going to be looking at unit cells that are pretty common in metals and ionic solids and so forth, and try to analyze how those unit cells work and how efficient the packing is in that unit cell.